All right, using Riemann sums and infinite limits to get exact area. Do change on the review that I handed out in class all of these formulas. These four formulas right here were all written incorrectly, so change them on your review if you haven't already. We did mention that in class. But moving on, we're going to use this limit and these formulas and everything on the review I will give you in class. And my function for number 6 is the x cubed plus 2 function, and I'm going to be doing this limit right there. The limit as n approaches infinity of all of that mess. All right, and the one formula I will not be giving you is the formula for the delta x. I'll give you everything else, and it's just a matter of you being able to use it successfully without screwing up. So delta x is still b minus a divided by n, and in this problem we're doing the area from 0 to 4, so that would be 4 minus 0, and in this case we don't have a number of subdivisions to plug in for n, and so my delta x is just 4 over n, and that 4 over n is going to replace the 4 over n, the delta x right here, and then I need to find my x sub I, and x sub I is a, which in this problem is 0, plus my delta x, which we just determined was 4 over n, times I, and when you clean that up, that becomes 4I over n, and the 4I over n is going to replace the x sub I right here, and so now, and I'm going to have a slight grammar error in my summation. I'm going to leave off the I goes from 1 to n, but it's f of x sub I, which is 4I over n, times delta x, which is 4 over n, and now I've got to clean up f of x sub I, f of all of this stuff, and so I'm going to come over here on the scratch paper and I'm going to figure out what is f of 4I over n. So f of 4I over n means we're just going to plug 4I over n for the x in my f of x formula. So it will be the quantity 4I over n cubed plus 2, which when you cube out 4I over n, you get 64I cubed over n plus 2 over n cubed plus 2. So now I replace f of 4I over n with all of that stuff, and so I will have the sum of 64I cubed over n cubed plus 2 times 4 over n. Then we'll take the 4 over n and we'll distribute it through this set of parentheses, which gives me the sum of, let's see, 64 times 4 is 256, I cubed over n to the 4th, and 2 times 4 over n would just be 8 over n. Then what I'm going to do is, because I've gotten rid of all the multiplication right here, I can break apart this summation into the sum of 256 I cubed over n to the 4th plus the sum of 8 over n. And ultimately what I'm trying to do is create one of these four summations, or maybe multiple. Actually, I have two of them here. And the ones I'm looking at is I have the sum featuring an I cubed. So I see this I cubed, meaning I'm probably going to steer towards this one. This one doesn't have any i's in it, so that's going to be the sum of a constant, and so I'm steering towards those two, and to make that happen, to get those two summation formulas, I'm going to take out all of my constants, which would be 256 and n to the 4th, because both of these summations are as I goes from 1 to n. So I is the variable in the i's of these summations. So I'm going to factor out the 256 over n to the 4th, and then I'm going to pull out the 8 over n. And when I do that, I will have 256 over n to the 4th times the sum of just I cubed as I goes from 1 to n, plus, and this one I'm going to take that 8 over n out, the sum of the sum as I goes from 1 to n, and I'm only left with a 1 on the inside. I took everything out, so there's a 1 as a placeholder. And then finally, we can replace these two summations, the sum of I cubed and the sum of a constant as I goes from 1 to n, with these formulas right here. Cn and this big one right here. So we're going to plug both of those in the place of these summations, which gives me 256. And actually, I'm going to pause the video and write these down. So I'm just going to substitute those in. That gives me those two, and then I'm simply going to multiply these two fractions together. I have 256 over into the fourth times this thing. That's going to be 256 n squared, n plus 1 squared over 4n to the fourth. And this one, 8 over n times 1n, would be 8n divided by n, and you are free to divide out and cancel those n's if you want. Then if you remember a long time ago, this summation, we're doing the limit as n approaches infinity. So now that I've cleaned up and I've gotten rid of all the summation notation, I can now go back and address that limit as n approaches infinity. And in these problems, if you are starting with a polynomial, which we are, the function was the polynomial x cubed plus 2. If you have a polynomial and you're using this approach, you will always end up with an infinite limit. Dadgummit, quit jumping up! There. You will always end up with an infinite limit where the top degree is equal to the bottom degree, so you can divide the coefficients. So if at this point your top and bottom degrees are not equal and you started with a polynomial, then that means you've messed up. In this case, I have 256 n squared times n squared. That would give me a 256 n to the fourth over 4n to the fourth. So that first fraction is going to approach 256 divided by 4. The second one, that's 8n over n. You divide their coefficients, that'll be plus 8 over 1. And you can throw that in a calculator, divide that out by hand, however you want to do it. And you will get 72 when you punch that in, and that would be the answer to this problem, which these take forever. Lots of places for you to mess up. Just be very careful with your work. And sadly, number 6 is the easier of the two when you look at number 7, because number 7, we're starting at 1 instead of 0 and having an initial value, or your a value being 1 and not 0, makes it a lot more difficult. So I'm going to go ahead and set this one up really quick. I'm going to pause it and set it up, and then we'll start working out the algebra. All right, there's our initial setup. I found my delta x, 3 minus 1 over n, which is 2 over n, and I've replaced the delta x here with 2 over n, and then x sub I is a plus your delta x times I, which cleans up to 1 plus 2i over n, which went in right here. And then finally, our last step in the initial setup is that I need to find f of 1 plus 2i over n, which means I'm going to plug 1 plus 2i over n in for x right here, which will give me all of that stuff squared minus 1, and then we have to fully expand that, which, remember, now this is like algebra 1 level stuff here, but don't brain fart. You have to actually expand 1 plus 2i over n completely. Don't just square the individual pieces. And there it is expanded. So I'm going to take all of this stuff, the 4i over n plus 4i squared over n squared, and that's all going to replace f of 2i over n, giving me this summation. So 4i over n plus 4i squared over n squared, and then all of that still times the delta x of 2 over n, and then I'm going to distribute the 2 over n. So we'll take that 2 over n, we'll distribute it through here, which would give you this. Distribute the 2 over n, and I went ahead and went one step further, and I broke my summation into 2 summations. And then, just like the last problem, I'm trying to steer towards one of these 4 formulas up here, and I see an I and an I squared, so I'm looking towards using the sum of I and using the sum of I squared, and I can do that when I take out the constants of 8 over n squared and 8 over n cubed. So when I take those 2 constants out, I will have the sum of only I and I squared as I goes from 1 to n. And now that I have those, I can finally replace these 2 with the formula for the sum of the first n integers and the sum of the first n squares, which is n plus 1 over 2 for the first one, and n plus 1 2n plus 1 all over 6 for the second one, and then the 8 over n squared and 8 over n cubed will just come down for the ride. Times all of that. And just like the last problem, I would rather have this written as a single fraction, have each of these written as a single fraction rather than a product. So that would be, for the first one, 8 times n plus 1. I'll just leave as 8n plus 1. And the bottom is going to be 2n squared. The next one, 8 times n plus 1, 2n plus 1, all over 6 times n cubed. And then now that I've cleaned up my summations and I've used the formulas that go with those two, the sum of I and the sum of I squared, I can now look at all of this and go back to the original limit, which was the limit of this sum as n goes from, or as n goes to infinity. There it is. And as I said before, you should have a situation where your top degree is equal to the bottom degree, and if you expand my numerators, 8n times n plus 1 would give me 8n squared plus 8n. 8n times n plus 1 times 2n plus 1, we only care about the high power term, which would be 8n times n times 2n is 16n cubed. And if I continue to expand that, I'd have a bunch of other stuff that doesn't matter because I see the high power term and the degrees are equal. We will divide coefficients. So 8 over 2 plus 16 over 6, which is 4 plus 8 thirds, which ends up, when you get a common denominator, combining to 20 over 3. And there is your final answer. If you want to know if your answer is correct, you do know how to get areas with antiderivatives. So if we go back to the original problem, it was this, and you could, I'm not going to work this out in detail, but I'm just going to show you how you could check your answer really quick. You could actually look at that and do the antiderivative, which this is later on in the review, but if you do the antiderivative of x squared is x cubed over 3, the antiderivative of 1 is x, and then evaluate that from 1 to 3. So that'd be 3 cubed is 27 over 3 minus 3 minus, plug in 1, 1 cubed over 3 minus 1. And if you want to work that out really quick just to see what the answer should be, you can see that this antiderivative does end up giving you the same answer as that long process up here. So take advantage of the fact that you do know the shortcut way of getting these areas so you can check your answer on these more difficult problems.